So, today we're going to be talking about motion. In this video we're going to be able to describe the motion of an object by the position of the object in relation to the reference point. And we're also going to be able to identify the two factors that determine speed. Okay? Motion. You assume that people move because you see them move. But what really are you seeing happen is a person walking by a reference point. Okay, what is a reference point? The object or point from which movement is determined. As we see in this picture here, we know that the student is in motion as he's walking by a stop sign because he starts on the left and ends up on the right. Movement is relative to an object that appears stationary. What does stationary mean? In place, fixed, not moving. Okay? We know a stop sign is fixed, it doesn't move. You've walked by a stop sign, does the stop sign walk with you? No, it's in place, it doesn't move. However, a reference point can appear stationary. And what I mean by that is if you think about NASCAR and racing, okay? These are my two NASCARs. They're coming around the track, okay? They're side by side. Are they not moving? No, they're moving, right? But they appear stationary until cheese car 1 pulls ahead, right? That makes cheese car 2 now the reference point. They're moving, all of a sudden pulls ahead, the reference point. It appears stationary. How? Again, by which movement is determined. We know that cheese car 1 sped up now because cheese car 2 is in the relative same spot that they were before. Okay? Again, a reference point appears stationary. It doesn't have to be fixed in a spot, in a location. It just needs to be separate from the object that's moving. Alright? The most common reference point is Earth. Why is it the most common reference point? There are things everywhere we can use as stationary or appearing stationary. For instance, trees, buildings, cars, people, a basketball hoop, right? All those things are on Earth. For instance, what do you think a reference point would be for the sun setting? In this picture, we see that the sun's going down. How do we know that the sun is going down? We can use the horizon out there. But remember, is it the sun really moving? No, it's the Earth moving. But again, our reference point here is the horizon. Appearing stationary, we can tell the movement of an object. Okay? So what do we do with this now? We know that it helps us determine movement, and movement is motion. Motion is a change in position relative to a reference point. Alright, student starts over on the left, student ends on the right of the stop sign. He's in motion. With this, we can calculate the speed. Speed is the distance traveled in a given amount of time. You can see over a course of time, the student has moved. We calculate the speed by distance divided by time. Now, don't forget, we need units. And a unit for speed is meters per second. This is our standard unit. But we also know in the metric system we can also do kilometers per second, centimeters, no more miles, no more yards, metric system, don't forget. Now, it's time to use the formula to calculate the speed of this student. Again, speed equals distance over time. These are the two factors we need to calculate speed, distance and time. Our distance, we see the student starts at 0 meters. Our time, 0 seconds. 0 meters divided by 0 seconds, 0 meters per second. Looking at the second picture, our time is now 2 seconds, our distance is 2 meters. Put that into our formula. 2 meters divided by 2 seconds our speed equals 1 meter per second. Looking at our third picture, our distance is 4 meters, our time is 6 seconds. Speed equals distance divided by time. Speed equals 4 meters divided by 6 seconds. Our speed in the third picture is 0.66 meters per second. Each one of these is a snapshot in time. This is the instantaneous speed, the speed at a particular moment in time. 0 seconds, 2 seconds, and 6 seconds. Snap, snap, snap. Right? However, when dealing with speed, a lot of times we're not going to deal with these instantaneous moments. What we're going to look at in the big picture is the average speed. The total distance divided by the total time. We see that the formula is still the same as speed, right? Speed equals distance over time. However, now we're looking at the whole scope of it. Not those tiny little snapshots, but like the whole time. We see our snapshots here, right? 0 seconds, it was 0 meters per second. 1 meter per second, 0.66 meters per second. Those are our snapshots. But you walking down the street or walking in the hallway, we can figure out your average speed by doing your total distance divided by total time. Our total distance this student walked was 4 meters. Right? So we put 4 meters on top. The total time the student had been walking for was 6 seconds. Put 6 seconds on the bottom. So our average speed is 0.66 meters per second. However, not always going to be solving for just speed. So what can we do? We can use our triangle. Okay? Distance goes on top, time and speed are on the bottom. We know our speed formula is distance over time. Now with the triangle, all we need to do is we're solving for speed, so we're going to cover it up. Covering up speed allows us to see that distance and time are left over, just like we see in our formula. Now what if we had to solve for distance? What do? Cover up distance. You see that speed and time are left on the bottom. So what do? Distance, if we're solving for distance, we're going to take speed times time. Alright? If we need to solve for time, cover up time, what's left? We got distance and speed. So for solving for time, we're trying to figure out how long it's been. Take the distance divided by the speed. That's our first lesson on motion.